All right, we've looked just briefly at the definition of what a radical is, and now let's look at another way of expressing a radical. So in this section, we're going to look at writing expressions with or without rational exponents. Um, we'll lose negative exponents. We'll review the laws of exponents just quickly and use them with rational exponents. And then we'll do some higher end simplification of radical expressions. So whenever you have a rational exponent, or whenever you have a radical, I should say, you can re-express that as a rational exponent. Take a look at the example that I have here. So on the left-hand side, I have a, and then in the exponent, I have m over n. And that, I've said, is equal to writing a radical, and just take note of where everything is. The a looks like it's part of the radicand, the n becomes the index, and the m becomes the exponent of the a. So whenever I have a an expression that has a fractional exponent, I can rewrite it as a radical. Or vice versa. If I have, say, the square root of 25, I could rewrite that as 25 to the exponent. Right now, the exponent here is 1, so the top number would be 1, and the index is 2. The 2 would go on the bottom there. So what we want to do is be able to practice going back and forth. Here's another example, 4 to the 3 halves. I can express that as a radical. Here's my radical sign. The radicand is 4. The exponent of the 4 is 3. And the index here is 2. Square root, I can just leave it as it sits there. So here I'm changing from a fractional exponent to a radical. And I can go back and forth depending on how I need to simplify. And sometimes I'll need to go start here and end up there, or start here and end up there. It just depends on the question. Here's another one for you to try. The fifth root of 3xy all squared. So if I want to change that from a radical to a rational exponent, I'm going to write the radicand down, 3xy. And then, notice because there are multiple factors in that term, I put it in brackets. And then up here, my exponent. What goes up top? If you said a 2, that's correct. And the index goes on the bottom. So this radical is the same as this rational exponent, or this expression that has a rational exponent. Okay, we also can have negative exponents, and you've dealt with negative exponents before in other classes. And what you simply do with negative ones is you change them from, if they're on the numerator like this one, change them to the denominator. I should have an equal sign in there. Change them to the denominator, and then the fractional exponent becomes positive. Once it's positive, then I can take this and change it to a radical. Again, a is the radicand, the top number becomes the exponent, the bottom number is the index. All right, maybe pause if you want and try some of those questions in your textbook, and hit play again when you feel like you've got that concept down. Just a quick little review now of exponent rules and things that you've probably done in the past. Multiplying common bases, add their exponents. That's incorrect. I'm glad I caught that. Add their exponents. If I'm dividing common bases, subtract their exponents. If I have a power of a power, that's where I multiply the exponents. And if I have two factors inside, all raised to one exponent, I can raise each one separately to that same exponent. This should be an m there. That should be an m. Boy, I'm glad I looked through these. Similarly, if I have a quotient of two factors raised to one exponent, I can raise each of them to the n. So we can do these same rules with fractional exponents or rational exponents. So in this case here, if I'm multiplying 3 to the 2/5 times 3 to the 1/5, If I'm multiplying common bases, I can add their exponents. So 2/5 plus 1/5. So if I add those together, that's 2/5 plus 1/5 is 3/5. So I can simply write that as 3 to the 3/5. Or I could, I guess, rewrite it as the radicand's 3, the exponent is 3, and the index is 5. I guess I could go further and say it's the 5th root of 3 cubed is 27. I could simplify it that far too. Here's another one. This one, which law over here will apply? Looks like it's a power of a power, so I multiply these. So this would be 1 times 3 is 3, 3 times 5 is 15. So x to the 3/15ths, which I could express as a radical. I could put the 15th root here, the x there, and the exponent of x is 3. Okay, so that hopefully, and you may want to again pause and try some questions in your book, just practicing the laws of exponents with things that aren't as familiar as just integers, but that are fractions. A little tougher. Okay, so let's maybe try and apply these in simplifying radical expressions to try and help me figure out what the answer to this would be. So let's maybe try this first one in a couple of different ways. If it says the 4th root, what I'm looking for are 4 things inside that are identical, and I can bring one out. If I have y to the 8th, that means I've got 8 y's. There's my 8 y's. If I have 4 inside, I can bring one out. I have another 4, I can bring a second one out. And inside the radical now there's nothing left, so again I don't even need to write that. It would just be y squared. Now that's one way I could do the question. That seems a little bit tricky though, maybe. I don't know about tricky, but a little bit labor. Why don't we see if we can try this a different way? And maybe let's change it into a fractional exponent. So it'd be y, and then the top number up here is whatever the exponent is, and the index is always on the bottom. Hey, there I've got a fraction that I can simplify. 8 divided 4 is 2. Y squared. Hey, same answer. So I could go through things two ways, but I can use this idea of changing my radical to a fractional exponent, and that'll help me maybe simplify things. Let's try that with this one here too. Oh, now here though, I've got a problem in that I have 2 terms inside here. And if I have 2 terms, like in this case here, it was just one term, one factor raised to the 8th. Here I don't have that. Oh, maybe let's try something else. So it's the 12th root. I guess one thing I could do is I could separate these. Whenever you deal with radicals, if you have 2 things that are being multiplied inside, I can take the first one and take it to the 12th root, and then I can multiply that by the second one, raised, or taking the 12th root of the second one. Okay, so that's a radical law that I can do that. If I have a product of 2 things, I can do each one separately. So here, changing these ones to fractional exponents, it'd be 3 over 12, and y would be 6 over 12. Or in other words, x, if I simplify that, would be to a quarter, and y would be to 1/2. And that's probably where I would leave that question. Yeah, there's other ways I could do that, but this is probably the most straightforward way. Let's try one last one, and this one might uh, might hurt us a little bit or hurt me a little bit. We'll see. We'll see how it goes. Okay, so I have the 4th root of 7 times the square root of 3. Since they're different indices, I can't just put those things together and call it the 4th root of 21 because this isn't the same kind of root. But I could change, and so I know my exponent here in both cases are 1. So this would be 7 to the 1/4 and times 3 to the 1 the index isn't written, so it has to be a 2. So I could rewrite those like that. Now I wonder if there's a way that I could do some more simplification there. Like perhaps I could write this as 2/4 times 3 to the 2/4. If I have this, it looks like they both have a common thing of 1/4. Like they each have a quarter. So this one's got 2/4, but at least has 1/4. So maybe what I could do is, um, it almost seems like you factor out a 1/4. I don't know if that's a good way of saying it, but that's almost what you do. So you leave the 7 here, times 3, and you raise that to a 1/4. But now I have a problem here in that this one was 2/4. If I take a 1/4 out, I guess I'm left with a 2 there. Let's just confirm that that works. That seems a little bit odd to me, but let me just see if that works. Power of a power, so I'd have to raise the 7 to a quarter. That's what I did. And I'd have to raise the 3 squared to a quarter. And if I do that, 2 times a quarter is 2/4. Yeah, that's, it seems just a little bit odd. But that's something that you can do. And it's not really factoring out, but you're looking for a common factor that each of these exponents would have. And if a quarter is one of them, I can almost, it's not factoring, but that's sort of the mindset. So I can take the quarter out, and now I'm left with 7 times 9 squared, which is, or 7 times 3 squared, which is 9. 7 times 9 is 63. So I have 63 to the 1/4, which if I want to rewrite it as a radical, I could say it's the 4th root of 63. Interesting, interesting. That's quite a little bit of work to get to that point. Let's try this last one, and I think it's a similar kind of concept that we'll have to look at. I see there's fractions here. Let's rewrite them all as sixths. So 4/6, 3/6, and z is already 5/6. And let's take that factor kind of idea, and we'll take 1/6 out, whatever the denominator is. So this one would stay as x to the 4th, this one would be y cubed, this one would be z to the 5th, but all of those would be raised to the 1/6. Let's just go backwards and check. So if I multiply this 4 by 1/6, I get 4/6, 3/6, 5/6. Yeah, that works. And then finally, if I wanted to rewrite that as a radical, I can call it the 6th root of x to the 4th, y cubed, z to the 5th. Notice since there's a 1 there, putting a 1 on the outside here of all these won't make a difference. 4 times 1, 3 times 1, 5 times 1, it doesn't change them all. All right, so that was a little bit more exposure to radicals. We saw in this section that the big thing is I can change radicals into fractional exponents or rational exponents, and I can change them back and forth. And found that sometimes in the changing, that helps me simplify an expression. Try some questions.